So in this video we're going to work through some examples of calculating partial derivatives. So when you're calculating a partial derivative, what you do is apply all of the derivative rules that you've learned already in calculus, and the only thing that you change is you either hold the y variable as a constant if you're taking the derivative with respect to x, or you hold the x variable and treat it like it's a constant if you're taking the derivative with respect to y. Other than that, all of the techniques that you've learned for taking derivatives apply. So if I've got a function right here, f of xy equals negative x squared plus x cubed y squared plus 3y squared, and I want to take the partial derivative with respect to x. So I'm going to go partial with respect to x, which is also going to be a function of two variables. You walk through and you just take the derivative like you usually would, but you treat the y as a constant when you see it. So right here, the derivative of negative x squared is going to be negative 2x plus, for this next one, because we're taking the derivative with respect to x, we're going to treat y squared as if it's just a constant. So we're going to treat it like it's a coefficient on the x cubed term. So the derivative of x cubed is going to be 3x squared, but we're going to treat the y as if it were just a coefficient sitting in front of the x squared. So we're going to get 3 times y squared times x squared. And then for the last term, because it has no x in it and we're treating y as if it's a constant, 3y squared is a constant when taking the derivative with respect to x. The derivative of 3y squared is just going to be 0. The derivative of a constant is 0. So here's the partial derivative with respect to x. And then if we want a specific derivative, if we want to know the rate of change with respect to x at a specific point on this surface, we can plug in values for x and y and find derivatives at specific points. So partial derivative of x at 1, 0, we walk through, and everywhere we see an x, we replace it with 1, and everywhere we see a y, we replace it with 0, and then we just simplify. So we're going to get a negative 2 out of this. So if we're taking the derivative instead with respect to y, we just start off with our original function, minus x squared plus x cubed y squared plus 3y squared. The partial derivative with respect to y, which will be a function of two variables, x and y. We're going to treat x as if it's a constant because we're taking the derivative with respect to y. So treating x as a constant, the derivative of negative x squared is 0 plus, now we're treating x cubed as a constant, so we're going to treat it like it's the coefficient on y squared. We take the derivative with respect to y. The exponent will come down like it always does. So we'll get 2x cubed, 2 times the coefficient on the y squared term. Reduce the exponent by 1 plus, and then the derivative of 3y squared with respect to y is just going to be 6y. And then if we want the derivative at a specific point on the surface, we can plug in our x and y values. So if I want to know the derivative when x is 1 and y is negative 1, I just pop those numbers in. So 2 times 1 cubed times y plus 6 times y plus 6 times y is negative 1, and then simplify. Here we get a negative 2 minus a 6 is a negative 8. So another example, take the derivative of f of xy. We have a function of two variables. Better put my cheater readers on, things are looking fuzzy right now. F of xy equals e to the cosine of x times y minus x over y. And we're going to take the derivative with respect to x first. So it says compute both partial derivatives. So we can also use that partial f partial x notation and we'll get a function of two variables out of this when we do. Or I can just write partial f partial x. Or I can write f sub x. So lots of ways that we can write this. So we don't want to forget any derivative rules that we have learned so far. So when we're taking the derivative with respect to x, we're really going to treat the y as a constant. So if I want to, I could write this as yx if it helped me to think about it. Y is going to be treated as a coefficient on x. just a constant. And x over y, we can think of it as minus 1 over y times x, where 1 over y is going to be treated like it's just a constant coefficient on variable x. So right here, the derivative of e to the crap is just e to the crap, so e to the cosine of yx or xy, times, then you would need to use the chain rule, because I have a function inside of a function. We have the cosine function, we have e to the x composed with the cosine function. So the derivative of cosine is minus the sine, so we would get minus the sine of y times x. But then we would need to use the chain rule again, because inside the cosine function there's a y times x. And the derivative of y times x with respect to x, where we're treating y as a constant, is just going to be y, right? If you took the derivative of 2x, you would just get 2, you would get the constant. So I'm treating the y just as if it were a 2 or any other constant. The derivative of y times x is y with respect to x. And then I can roll along, minus, from the minus right here, and we're treating the 1 over y as a constant on x, so the derivative of 1 over y times x with respect to x is just going to be 1 over y. And then we can look at this. We might want to rewrite things just to clean it up, so maybe pull that negative out front. Negative, whatever makes it look cleanest, negative e to the cosine of xy times the sine of xy times y, and then 1 over y. So if we take the derivative now with respect to y, that means treat x as though it were a constant. So let's go ahead and rewrite the function. F of xy equals e to the cosine of xy minus x over y, which I can also think of out as being x times y to the negative first power. So if we're taking the partial derivative with respect to y, we hold x constant. So the derivative of e to the crap is just e to the crap. But I have function composition, so I need to use the chain rule. So now I need to multiply by the derivative of the cosine, which is going to be minus the sine of x times y. But I have stuff inside of the cosine, so I have the triple function composition here. So now I need to take the derivative of x times y, but when we're taking the derivative with respect to x, when we're taking the derivative with respect to y, we're holding x as a constant. So the derivative of x times y is just going to be x minus, we're taking the derivative with respect to y, so we hold x as a constant, so that we treat it like it's a coefficient on y, so we're going to get x in the derivative. The exponent, negative 1, will come down. We'll get negative 1 times minus x is plus x times y, and then subtract 1 from that exponent, we get a negative 2. So there's that derivative. So we'll do one more example. So I tried to come up with a creative function that was nasty. So I mean, we could make it nastier, but I thought this one was nasty enough. The natural log of the square root of the product of the cosine function and the sine function. And of course, we would need to recognize that because we have a natural log, we need the stuff inside the natural log to be greater than 0. I have a square root, I need the product of the cosine and the sine to be greater than or equal to 0 inside of here. So ultimately, I want to recognize, even though I don't need to do anything with it necessarily, I want to recognize that the cosine of x times the sine of y for this function, the natural log of the crap, this product inside of here is going to need to be greater than 0 in order for us to be able to take the natural logarithm. So the derivative of this, if we do it first with respect to x, so let's do partial f, partial x. So we're holding y constant. So all the normal derivative rules apply. The derivative of the natural log of crap is going to be 1 over the crap. Oh, there we go. My pin's freezing up on me. Hopefully we make it through the video. So the derivative of the natural log of crap is 1 over the crap, so we get 1 over the square root of the cosine of x times the sine of y but then you have to multiply by the derivative of the crap that's inside the logarithm by the chain rule. So, right, this is a square root, so we can think about him as being raised to the half power. So we'll get derivative of this is going to be 1/2 the stuff inside the square root, which is just the cosine of x, times the sine of y, and then we subtract 1 from the 1/2 to get a negative 1/2 sitting here. But I have to use the chain rule again because I have stuff inside the square root function, so multiplied by, and we're taking the derivative with respect to x, so we're treating sine of y as if it's just a constant coefficient on cosine of x. So we're going to get the sine of y times the derivative of cosine is minus the sine, and minus the sine of x, because we were taking a derivative with respect to x. And maybe we could clean this up a little bit, but there's not a whole lot of cleaning that we can do to it. There is some, right? Here's a square root, and we've got this, so definitely could bring this down and do some cleaning, right? 1 over, we'll get a square root in the denominator, so it looks like we'd get a cosine x sine y. When we bring this down, we're going to be times that 1/2, so there's going to be a 2 down here. And then what do we have in the numerator? Minus sine x sine y. Yeah? And then we get a negative 1/2 sine x over cosine of x is a tangent of x. And then it looks like I have a sine y over a sine y. So I guess it was worth cleaning that up. This is where you say, I hope I didn't make a stupid mistake someplace, right? That can always happen. All right, partial derivative with respect to y. So let's go partial derivative with respect to y. So natural log of crap is again going to be 1 over the crap. So it's just going to be 1 over the square root of cosine x sine x times, now we need to use the chain rule, so the derivative of the square root stuff on the inside of the natural log function, so the 1/2 is going to come down, times cosine x sine y, and this is going to be to the negative 1/2. So again, we'll bring this down to make the exponent positive, which will give us a square root times the square root. And we need to make sure that looks like it's a y. It didn't look very much like a y, times. And then the chain rule says now we have to take the derivative of the stuff inside the square root function. We're taking the derivative with respect to y. So we're going to hold a cosine of x as if it's a constant. So we'll get cosine x times the derivative of sine y is going to be cosine of y. And then cleaning things up just a little bit, we get a cosine x sine y in the numerator, and we get the square root times the square root of stuff times the square root of the same stuff in the denominator is going to give us a cosine x sine y in the denominator. And that looks like it's just going to equal, let's see, cosine x, that should be a cosine y right here. The numerator should be cosine x cosine y. Cosine y. And so we get cosine x over cosine x is 1, as long as cosine's not equal to 0. And cosine y over sine y looks like a cotangent of y. So that cleaned up pretty nicely.